One hand watches the other. Dynamic multi-agent cooperation for sample-efficient bimanual manipulation in dynamic environments. All policies shown in this video were trained on 5 demonstrations or less. Multi-stream robot policies like MIDI-gap and MSG achieve unparalleled sample efficiency. However, so far they were confined to static environments and to single-arm robots. In this work, we present DynaMAC, a lightweight and policy-agnostic multi-stream framework that unifies manipulation in dynamic environments with bimanual manipulation and multi-agent coordination. DynaMAC not only learns diverse bimanual tasks from few demonstrations, but it generalizes zero-shot from static demonstrations to dynamic environments. It is also robust to perturbations and dynamically recoordinates, making it a promising approach for human-robot collaboration as well. So, how does it work? Multi-stream learning decomposes the trajectory distribution for solving a given task into multiple object-centric models called streams. During inference, these streams are transformed using the workspace geometry and fused into a single policy, shown here in green. But typically, this approach only works with static object frames. This is because it assumes those frames to be exogenous, meaning they are not affected by the robot's actions. Using dynamic frames leads to policy collapse as soon as the robot manipulates the object, violating this causal assumption. However, we can estimate such kinematic links between robot and object from the precision of the corresponding streams. While the MAC is grasped, its stream exhibits a very high precision. We then temporarily mask out these kinematically linked frames, restoring the causal assumption. And we add virtual end effector frames to provide additional spatial reference. Having solved multi-stream learning for dynamic scenes, we then reduce bimanual policy learning to dynamic multi-stream learning. Each robot's end effector pose is the potential task parameter for the other robot. Here, the left arm establishes a rendezvous point and then guides the right arm towards handover. Crucially, this causal structure is learned from the demonstrations and not imposed a priori. Instead, leader-follower relationships can change dynamically across the task horizon. We evaluate our approach on a diverse set of simulated and real-world tasks. For manipulation in dynamic environments, we introduce DynaBench, a benchmark built on RLBench, inheriting the latter's task diversity, extendability, and automatic data generation. We find DynaMAC to generalize zero-shot from static demonstrations to dynamic environments. We also evaluate DynaMAC on RLBench 2, a bimanual extension of RLBench. We find strong few-shot policy performance across tasks requiring spatial, temporal, and physical coordination. DynaMAC significantly outperforms baselines such as diffusion policy that were trained on 20 times more demonstrations. Moreover, we integrate these bimanual tasks into DynaBench and evaluate bimanual manipulation in dynamic environments, again finding strong zero-shot transfer of our method. In contrast to baseline methods, DynaMAC also dynamically recoordinates when perturbing the rollout of either robot arm. This robustness towards inconsistent behavior of a collaborator makes DynaMAC an interesting approach for human-robot collaboration. We verify our simulated experiments on a real bimanual Franka-Amica setup. We use a single RealSense RGBD camera to estimate task object positions using a dyno-based keypoints encoder. Recreating the simulated challenges, We evaluate object storage, articulated object interaction, asymmetric collaboration, joint lifting, and object handover. As in simulation, we find strong few-shot performance in the static conditions, as well as zero-shot generalization to perturbations of either robot arm and to environment dynamics. Overall, DynaMAC is robust. Policy failures are rare and mostly caused by perception errors, most commonly faulty depth measurements. Finally, we demonstrate DynaMAC's potential for human-robot collaboration by modifying the handover task. As you can see here, our method adapts competently to the inconsistent handover locations proposed by the human collaborator. Thank you for watching. You can find additional information as well as our source code on our project website.